Hi all, this is Satyanarayanan from School of Electronics Engineering, VIT Chennai campus. In this video lecture, we will cover analysis of discrete time systems. Okay, so discrete time systems can be analyzed using two transforms, Fourier transform or discrete time Fourier transform, that is DTFT, and the other transform is Z transform or Z transform. So let me explain how we will be approaching this lecture slides. In this lecture, we will consider one example problem for each of the transform and we will try to solve the problem. On our way to solution, we will be discussing some properties, that means some transform properties and transform pairs. So by the end of the problem, or by the time we solve the problem, we will understand the problem and also learn some important transform properties and transform pairs. Yes, this is very important. So the study material or reference book is Signals and Systems by Alan V. Oppenheim. Okay, so let's move to the problem straight away. Yes, so consider a causal LTI system that is characterized by the difference equation y of n minus 3 by 4 y of n minus 1 plus 1 by 8 y of n minus 2 is equal to 2 x of n. So we are asked to find frequency response h e raised to the power j omega and impulse response h of n for the system. Therefore, so this is the difference equation characterizing the LTI system. Yes. So why this is called difference equation? Because this refers to a discrete time system. So it is called difference equation. So in the case of continuous time system, it will be differential equation which involves dy of t by dt, t square y of t by dt square and so on. And the system does not, the output of the system does not depend on any future values of the input and hence the name causal. Okay, let us focus on our goal. So we need to find the system function or the frequency response h e raised to the power j omega first. So once we find that, then taking inverse DTFT on the frequency response will give the impulse response of the system. Okay, so the first step, we should take discrete time Fourier transform on both sides of the difference equation. So therefore, yes, so taking difference equation, taking DTFT on the terms in the difference equation will require the understanding of the time differencing property, which means, so when it is y of n, its DTFT is y e raised to the power j omega. It's very simple. But what will be the DTFT of y of n minus 1? So the DTFT of y of n minus 1 is e raised to the power minus j omega times y e raised to the power j omega. So for this minus 1, in the n minus 1 in the place of n, so therefore there is a negative exponential term outside. Of course the minus 3 by 4 should be carried here. So for n minus 2, it will be e raised to the power minus j 2 omega times y of e power j omega, and the plus 1 by 8 term comes here, then is equal to 2x e raised to the power j omega. So therefore, using the time differencing property, we have expressed the relationship between the input and output that was originally characterized in terms of y of n and x of n as x of e power j omega and y of e power j omega. So the next step, yes, now we have y of e power e raised to the power j omega terms on the left and x e power j omega term on the, of course it's the only term on the right. So just to group all the terms, so this becomes 1 minus 3 by 4 e power minus j omega plus 1 by 8 e power minus j 2 omega times y of e power e raised to the power j omega is equal to 2x e power j omega. Okay, so now just looking at the question again, we need to find h e power j omega, and we have nicely we have terms on both sides of the expression multiplied by y and x respectively. So h e power j omega or h e raised to the power j omega is y e raised to the power j omega divided by x e power e raised to the power j omega. So a simple cross multiplication will give h e raised to the power j omega, something like this. So h e raised to the power j omega, which is the frequency response of the given system, is equal to y capital Y divided by capital X. So that can be expressed as 2 divided by 1, of course there is a bracket missing here. Okay, 2 divided by 1 minus 3 by 4 e raised to the power minus j omega plus 1 divided by 8 e raised to the power minus j 2 omega. So first part of our answer is here. So the next step is to find the impulse response h of n. So since h of n and h e raised to the power j omega form a DTFT pair, which means if you take DTFT on h of n or small h of n, you will get capital H of e power j omega. And on the other hand, if you take inverse DTFT of h capital H e raised to the power j omega, you will get h of n. So here we need impulse response small h of n, and we have already found capital H e power j omega. So it's straightforward. The impulse response h of n is equal to inverse DTFT. So I have just this is to represent Fourier inverse of this. So now we are just writing the h e raised to the power j omega term. So this term, yes. So yeah, so we need to do factorization because with this expression we couldn't find a suitable transform pair so that we can directly find Fourier inverse. So we are for the sake of convenience, we are writing them, splitting this denominator into two terms. So therefore, when we factorize, it becomes 1 minus 1 by 2 e raised to the power minus j omega times 1 minus 1 by 4 e raised to the power minus j omega. So now the next step is to express this term as a summation of two fractions. So therefore, we need to use partial fraction. So when we apply partial fraction, the term inside the square bracket becomes summation of two terms. The first term is 4 divided by 1 minus 1 by 2 e raised to the power minus j omega, and the second term is minus 2 divided by 1 minus 1 by 4 e raised to the power minus j omega. So now this can be using the linearity property. This can be written as 2 Fourier inverse, and the constants can be taken outside. So therefore, from the first term, 4 is taken outside, and this becomes Fourier inverse of 1 divided by 1 minus 1 by 2 e raised to the power minus j omega minus 2 times Fourier inverse of 1 divided by 1 minus 1 by 4 e raised to the power minus j omega. So now we can just recollect the transform pair. Yes. So for time being, let us look here. The Fourier inverse of 1 divided by 1 minus a e power j omega minus j omega is equal to a power n u of n. Of course, there is a condition provided the a modulus of a is less than 1, and here it is for both the cases, even 1 by 2 and 1 by 4, it is satisfying the constraint. So Fourier inverse of 1 divided by 1 minus a e raised to the power minus j omega is equal to a raised to the power n u of n. So therefore, for the first term, the constant 4 has to be brought. Then this becomes 1 divided by 2 raised to the power n u of n. The second term minus 2, 1 divided by 4 raised to the power n u of n. So this, therefore, we have obtained the impulse response of the system. So why the impulse response of a system is important? Because any system, when characterized by an impulse response, gives an output which can be easily estimated, because the output is just the convolution of the input signal h of n with the impulse response h of n. So given a system's impulse response, or upon finding the impulse response of a system for any given input, we can have an estimate of the output. Just to summarize what we have done in this problem, a system characterized by its difference equation is given, and we are asked to find the frequency response h of omega, or h is e raised to the power j omega, and the impulse response h of n. First, we applied the DTFT on both sides of the equation. Using time differencing property, we obtained the expression for h of e power j omega, which is the frequency response. Then the inverse DTFT of the frequency response is obtained, which is the impulse response of the system. So now we will move to the problem on Z transform or Z transform. So conveniently, I will be mentioning that as Z transform. Yes. So this is for question 2. Consider an LTI system that produces the output y of n is equal to 10 raised to the power 1 divided by 3 raised to the power n minus 9 1 divided by 2 raised to the power n u of n. Okay, this u of n is the unit step function, discrete time unit step function. When the input is x of n is equal to 1 divided by 6 raised to the power n u of n. determine the constant coefficient difference equation that characterizes the system. Yes, this is a bit tricky. Like the previous question we saw, they have given a system's difference equation or a system's constant coefficient difference equation and asked and we were asked to find the frequency response and the impulse response. But here they have given a pair input output pair. So x of n, when it is equal to 1 by 6 raised to the power n u of n, we are getting an output which is given. So therefore for this combination, this is one combination, and from just this one combination you are supposed to find the constant coefficient difference equation. And yes, there is a method. So the first step, we since x of n and h of y of n are given, sorry, x of n and y of n are given, we can find their z transforms or z transforms, capital X of z and capital Y of z. So once we have that, we can actually determine the system function h of z, and since we will have the fraction y of z by x of z, we can do cross multiplication and arrive at the difference equation. Let us go step by step. There it is. So determine the constant coefficient difference equation. That z transforms of the input and output are x of z equal to 1 divided by 1 minus 6 z inverse, and for y of z it is 10 divided by 1 minus 1 by 3 z inverse minus 1 divided by 1 minus 2 z inverse. Of course these are z transforms, so we have to mention the region of convergence. Okay. So the region of convergence and the standard z transform pair is what you need to know in prior to write the expressions for x of z and y of z given x of n and y of n. So now the z, there is a z transform pair basically which is gives a power n u of n. If you take z transform, you will get 1 divided by 1 minus a z inverse. So therefore in x of n you just have one term, so you have that term, and the region of convergence is quite standard, modulus of z. Okay, z is a complex number, so the modulus of z should be greater than a in terms of a power n u of, in the case of a raised to the power n u of n. In the case of 1 by 6 raised to the power n u of n, it is the modulus or the magnitude of z should be greater than 1 by 6. Yes. In the case of two terms, first, okay, the constant is written here, and it, because of 1 by 3 we are writing it as 1 minus 1 by 3 z inverse minus 9 divided by 1 minus 1 by 2 z inverse. The region of convergence is the magnitude or the modulus of z lies right in between 1 divided by 2 and so 1 divided by 3. So given x of n and y of n, the first step is to find x of z and y of z. We are using the standard z transform pair. Next. So we have y of z, x of z, so straight away we can write h of z. So h of z is just the ratio of y and x. So y of z I'm writing, and x of z, just the reciprocal of x of z is written here. So the next step, further h of z can be expressed as Okay, here the two terms are merged, or just added these two terms. In fact, the second term is subtracted from the first term. So we have a term in which the numerator is 1 minus 2 z inverse divided by 1 minus 1 by 3 z inverse times 1 minus 1 by 2 z inverse. So times that second term remains the same. So next, so we have combined the two terms. 1 minus 2 z inverse times 1 minus 6 z inverse. So the denominator remains the same. So now next, it is just multiplying these two terms. So we have three terms. A constant term is 1 minus 13 by 6 z inverse plus 1 by 3 z power minus 2. So in the denominator, 1 divided by 5 by 6 z inverse plus 1 by 6 z power minus 2. So we know h of z, of course, yes, this is z transform, z transform. Therefore, the ROC, region of convergence, is modulus of z greater than 1 divided by 2, because there are only two terms in the denominator of h of z expression, 1 divided by 3 and 1 divided by 2. The term modulus of z greater than 1 by 2 also covers modulus of z greater than 1 by 3. So the region of convergence can be conveniently expressed as this, greater than 1 by 2. So therefore, h of z is the ratio of y and x. Therefore, y divided by z, sorry, y of z divided by x of z is equal to 1 minus 13 by 6 z inverse plus 1 by 3 z power minus 2 divided by 1 minus 5 by 6 z inverse plus 1 by 2 z power minus 2. So just to remind that we need to find the difference equation of the system. So it's quite straightforward. Now when we cross multiply the term, then we will on the left hand side we will have y of z terms, and on the right hand side we will have x of z terms. So upon cross multiplying, we nicely have y of z terms to our left, x of z terms to our right. So now multiply to the individual terms. So this becomes y of z minus 5 by 6 z inverse y of z plus 1 by 6 z power minus 2 y of z is equal to x of z minus 13 by 6 z inverse x of z plus 1 divided by 3 z power minus 2 x of z. So now if we take the inverse dt of t, straight away we will get the difference equation. Also we need to use, oh sorry, it's not inverse dt of t, it's inverse z transform, because this is z transform, so it's y of z. So therefore if we take inverse z transform, we will get y of n terms and x of n terms. So, and also we need to apply the time differencing property of the z transform. Okay. So using time differencing property, the first term is simple, y of n, second term is minus 5 by 6 y of n minus 1 plus other term is 1 by 6, third term is plus 1 by 6 y of n minus 2 is equal to x of n minus 13 by 6 x of n minus 1 plus 1 by 3 x of n minus 2. So therefore we have obtained the constant coefficient difference equation of a system. So this is called constant coefficient difference equation because see, for every term, or the term y of n with no delay or the term y of n with delays, the coefficient is always a constant, which means there is no n terms there. So therefore, we have arrived at the answer. So just a recap of what we have done. So we are given with x of n and y of n, one pair of x of n, y of n, and we are asked to characterize the system in terms of its difference equation, constant coefficient difference equation. We applied z transform on x of n and y of n and obtained x of z and y of z. So using x of z and y of z, we expressed the ratio which is h of z, which is the transfer function of the system. And the same y of z divided by x of z ratio can be used to obtain the difference equation of the system. So therefore we did cross multiplication, had arranged two terms, sorry, arranged y of z terms on our left and x of z terms on our right. So then taking the inverse z transform and using the time differencing property, we obtained y of, so obtained the constant coefficient difference equation. So we could see we have now solved problems one each for discrete time Fourier transform and Z transform. They look almost similar. Yes, they do. They are. But the Z transform is more in general, which means the Z transform, when we put Z equal to e power j omega or Z equal to e power j omega, the Z transform converges to discrete time Fourier transform. Or when Z equal to e power j omega, Z transform is same as discrete time Fourier transform. So thanks for watching this video. So in case you have any queries, feel free to write an email to me. Thank you.